the dynamics of the falling paper tube challenge, wherein we have a toilet paper tube, which we'll say has mass m and outer radius capital R and inner radius lowercase r, and the rest of it being, paper in this region. And what we want to do is find the ratio of heights such that when we drop the roll and we let it unroll from height capital H, and we drop it without unrolling and let it fall from height lowercase h, we want to find the h over h such that the times are equal. In other words, when we drop both of them at the same time, they hit the floor at the same time. And this is going to be the dynamics approach, so we're going to do it by saying, let's take a look at our free body diagram. So there's our object, and here are our forces. Well, we certainly have gravity pulling downward with some force Fg, and some tension pulling upward, which I'll call Ft, and then the tube accelerates downward with acceleration A, and also spins up, or gains spin with angular acceleration alpha in that sense, and we're going to treat it as if it were rotating around the center of mass, and the center of mass were falling. So using Newton's second law in translation, we would have Fg minus Ft equals m times A. I guess we should use the correct m. So m times A. And then from the the rotational equation, we use the torque equivalent to this, and we find that Ft times the outer radius is I times alpha. And then finally, under the assumption that the roll is unrolling smoothly, we'd also have a connection that A is alpha R. So those are our three equations, and now we need to do a fair bit of basically just algebraic junk to make that work. So let's go down and do that. We no longer need that bit, but we'll keep this on. And what we'll do is we'll take that second equation and we'll solve it for, we'll say that Ft times R equals I A over R. And this way I'm eliminating alpha because alpha is not of interest to us so much as the accelerations, which will tell us how fast it falls. And this, of course, becomes that Ft R squared equals I A. From this first equation, we find that Ft equals Fg minus ma, or of course just m times g minus m times a, which we can now put this into here, and we find that mg minus ma times r square equals I times a. Then we can just distribute, so we'll say something like mgr square minus mar square equals I alpha. I times a. So we can bring the a terms to one side, so we'll have mgr square equals mar squared plus ia. We can factor out the a, and we'd have mr squared plus I. That leads us to our final answer, as it were, that the acceleration is mgr squared over mr squared plus I, which is probably better written as some factor mr square over mr square plus I times g. And I'm going to go a little further with that and even call this just 1 over 1 plus k times g, using the idea that k is defined as as the rotational inertia over mr squared. And that just means I have to write less later on. So there you go. Now we're going to use the fact that both A and, of course, G are constant, and so we know that the height through which the object falls while unrolling is 1/2 AT square, and the height through which it falls when simply free falling is 1/2 GT square. And so the thing that we want, which is H over H, equals, and we can see that the halves cancel out and the T's cancel out, and we just get A over G, or 1 over 1 plus K. So we get a nice simple result. As a reminder, this would be something like mr squared over mr squared plus the actual rotational inertia. And as long as we set up that ratio, we measure this ratio, we would get the ratio we would need to get them to hit at the same time.